Hi students, how are you? In this session, we are going to discuss about class equation. In mathematics, counting is one of the most difficult tools. Now, we are going to introduce an equivalence relation on a finite set, measure the size of the equivalence classes under the relation, and then equates the number of elements in the set to the sum of orders of this equivalence classes. Now, let us start with the definition of conjugate. If A, B belongs to G, B is said to be a conjugate of A in G if there exists an element C in G such that B is equal to C inverse AC. In symbols, we can write B is conjugate to A as A tilde B. One can readily verify that the relation of conjugacy is reflexive, symmetric and transitive, and thus an equivalence relation on a group G. The equivalence classes are determined by this relation or referred to as the conjugacy classes of G. Let us verify it in this result. The result is conjugacy is an equivalence relation on G. The proof is, let A in G. What is the first property? It is reflexive. It is trivial since A is equal to E inverse AE, that is a conjugate to A. In symbols, we denote it as A tilde A. The second one is symmetric. To prove symmetric, we have to say that a conjugate to B implies B conjugate to A. Suppose if A tilde B, then B can be written as x inverse AX. B is equal to x inverse AX for some x in G, which implies A is equal to x inverse the whole inverse B x inverse. Let us take y is equal to x inverse in G, then A is equal to y inverse BY. That is, B is conjugate to A in symbols B tilde A. The final one is transitivity. To say it is transitive, we have to show that if A is conjugate to B and B is conjugate to C, then we have to prove A is conjugate to C. If A tilde B implies B is equal to x inverse AX and B tilde C implies C is equal to y inverse BY for some x, y in G. Then C is equal to y inverse BY is equal to y inverse into x inverse AX into y is equal to xy the whole inverse into A into xy is equal to z inverse AZ for some z is equal to xy in G. This is A is conjugate to C, in other words A tilde C. Hence, conjugate satisfies reflexive, symmetric and transitivity implies it is an equivalence relation on G. Let us find out the order of the conjugate element in the coming result. The result is conjugate elements have the same order. Let us prove this. Let x, y in G. Consider x and y is equal to Gx G inverse. That is, x and y are conjugate to each other. If x power n is equal to identity, then Gx G inverse the whole power n is equal to Gx G inverse into Gx G inverse into Gx G inverse n times is equal to G into x power n G inverse is equal to G identity G inverse is equal to E. Therefore, order of x is greater than or equal to order of Gx G inverse. Conversely, if Gx G inverse the whole power n is equal to identity, then G x power n G inverse is equal to identity. then it must follow that x power n is equal to identity. Therefore, order of x is less than or equal to order of g x g inverse. From this, we know that order of x is equal to order of g x g inverse, which is equal to order of y. Hence, we have proved here that conjugate elements have the same order. Until now, we saw the conjugate is an equivalence relation, then it should form an equivalence class. Let us name that class as a conjugacy class. Let us see the proper definition of it. The definition is, the conjugate class of A in G under this relation is called the conjugate class of A in G and is denoted by C of A, where C of A is equal to the set of x in G such that A tilde x. Suppose conjugate class of A in G, C of A has CA elements, then order of G is equal to sum of A in G CA. Some examples of conjugacy classes are here. See it. The examples: 3 conjugacy classes of symmetrics of triangle. See these pictures. 3 reflections SA, SB, SC. SA is reflection along the axis A, SB is reflection along the axis B, and SC is reflection along the axis C. Next, see this one. 2 rotations with respect to the angle 120 and 240, which is obtained by cyclically permute vertices. 1 trivial symmetry or not, which is obtained from do nothing. Now we will describe the conjugacy class in S4. Let us see the table here. The cycle type is 1 plus 1 plus 1 plus 1. Here, the element of the type is identity. The conjugacy class is identity. Here, there is only one element. So, the order of CA is here is 1. Next, see the cycle type. It's 2 plus 1 plus 1. Here, we are having the cycle 1, 2. This is the element of the type. Here, the conjugacy class is the cycle 1, 2, cycle 1, 3, cycle 1, 4, cycle 2, 3, cycle 2, 4, cycle 3, 4. Here we are having 6 elements. So, the order of CA is 6. Next, see, the cycle type is 2 plus 2. The element of the type here is the product of cycle 1, 2 and 3, 4. The element of the type is here the product of cycle 1, 2, cycle 3, 4. The conjugacy class is the product of the cycle 1, 2, cycle 3, 4. The product of the class the product of the cycle 1, 3, cycle 2, 4. The product of the cycle 1, 4, cycle 2, 3. Here only we are having 3 elements. So, the order of CA is here 3. Next, see, the cycle type is 3 plus 1. So, what is the element of the type? Is cycle 1, 2, 3. The conjugacy class is cycle 1, 2, 3, cycle 1, 3, 2, cycle 1, 2, 4, cycle 1, 4, 2, cycle 1, 3, 4, cycle 1, 4, 3, cycle 2, 3, 4, cycle 2, 4, 3. How many elements? 8. So, the order of CA is 8. The cycle type is 4. Then, the element of the type is cycle 1, 2, 3, 4. What are the conjugacy class? Cycle 1, 2, 3, 4, cycle 1, 2, 4, 3, cycle 1, 3, 2, 4, cycle 1, 3, 4, 2, cycle 1, 4, 2, 3, cycle 1, 4, 3, 2. How many elements? Yes, you are right. There are 6 elements. So, the order of CA is 6. Note that 1 plus 6 plus 3 plus 8 plus 6 is equal to 24. Cardinality of S4 as should be the case since conjugacy classes of a group G form a partition of G. Now we can see the relation of conjugacy class and the group. The notice, a group G is the disjoint union of its conjugacy classes. Moreover, the conjugacy classes of the identity element of G contains no other element of G. The next notice, a group G is abelian if and only if all its conjugacy classes contain exactly one element of the group G. Next one is definition of normalizer, which is similar to conjugacy classes. Let us see the definition. If A belongs to G, then n of A, that is the normalizer of A in G is the set n of A is equal to x belongs to G such that xa is equal to Ax. We know very well that normalizer is a subset of a group. Can you think, will it form a subgroup? Then let's verify it in this result. See this result. Prove that the normalizer of A is a subgroup of G. The proof. We know that normalizer of A is equal to the set of x in G such that xa is equal to Ax. Suppose that x comma y in n of A, which implies xa is equal to Ax and ya is equal to ay respectively. Now we have to prove that xy in normalizer of A and x inverse in normalizer of A. Now we will prove xy in n of A. So xy of A, it will be written as x into ya by the associate law. See here, x into ya will be written as x into ay because already we have seen that ya is equal to ay. Here again by the associate law, we will write xa into y. We have seen xa is equal to ax, so it will be written as ax into y. Again by the associate law, a into xy. This implies xy into a is equal to a into xy, hence xy in normalizer of A. Next we prove x inverse in normalizer of A. X inverse A is equal to x inverse A x inverse. Here we will add x inverse is equal to 1, so it won't change anything. So x inverse into Ax into x inverse is equal to x inverse into Ax into x inverse by the associate law. X inverse is equal to xa into x inverse. We have already seen that Ax is equal to xa. So the answer is Ax inverse. This implies x inverse A is equal to Ax inverse, hence x inverse in normalizer of A. Therefore, normalizer of A is a subgroup of a group G. The next theorem will show the relation between conjugacy elements and the index of the normalizer. The theorem is, if G is a finite group, then Ca is equal to order of G divided by order of normalizer of A. In other words, the number of elements conjugate to A in G is the index of the normalizer of A in G. Let us prove this. The conjugate class C of A consists exactly of all the elements x inverse Ax as x ranges over G. We shall prove that two elements in the same right coset of normalizer of A in G yields the same conjugate of A. Two elements in different right coset of normalizer of A in G gives rise to different conjugate of A. That is, we shall have a one-to-one correspondence between conjugate of A and right coset of normalizer of A. The case 1 is, suppose x comma y belongs to G and are in the same right coset of normalizer of A in G, then y is equal to nx, where n in normalizer of A. So, y inverse is nx the whole inverse, because already we have seen y is equal to nx. Here we will write this as x inverse n inverse. Both the side multiple with ay. The answer is y inverse ay is equal to x inverse n inverse ay. So, x inverse n inverse a into nx, because y is equal to nx, is equal to x inverse n inverse a n into x by the associate law, is equal to x inverse n inverse, the an is equal to na. So, x inverse n inverse into na into x is equal to x inverse ax. Therefore, y inverse ay is equal to x inverse ax. Hence, x and y are in the same conjugate of a in G. The case 2 is, suppose x and y are in the different right coset of normalizer of a in G. We claim that x inverse ax is not equal to y inverse ay. Suppose x inverse ax is equal to y inverse ay, pre-multiply by y, then post-multiply by x inverse, then we get y into x inverse ax into x inverse is equal to y into y inverse ay into x inverse. Y x inverse into a is equal to a into y x inverse. Then y x inverse in normalizer of a, which implies x and y are in the same right coset of normalizer of a in G. Contradiction 2, x inverse ax is not equal to y inverse ay. Thus, there is a one-to-one correspondence between the right coset of normalizer of a in G and the conjugates of a. We know that Ca is equal to the number of distinct element in conjugacy class of A is equal to the number of distinct right coset of normalizer of A in G, which is equal to index of normalizer of A in G, is equal to order of G by order of normalizer of A. Hence, it's proved. Finally, we came to the main part of this section, that is nothing but a class equation. If G is a finite group, then order of G is equal to summation runs over all the elements A in G, order of G divided by order of n of A. The proof is, we know order of G is equal to summation runs over all the elements A in G, Ca. By the previous results, we have Ca is equal to order of G by order of Na. So, the summation runs over all the elements A in G, Ca is equal to summation A in G order of G divided by order of n of A. Order of G is equal to summation A in G order of G divided by order of n of A. Hence, proved. Suppose the group have a non-trivial center, then the class equation is slightly differing from the previous one. For that, first we have to see the definition of center of a group. What is the definition of center of a group? It is the center eject of G of a group. G is eject of G is equal to the set A in G such that Ax is equal to Xa for all x in G. Now we know the center of a group. Then let us see the class equation for non-trivial center. The theorem is, let G be a non-trivial finite group whose order is a power of a prime P. Then the center of G, eject of G has more than one element. Let us prove it. First, observe that C of A is equal to singleton set A, if and only if A in eject of G. Thus, by culling out these elements, we may write the class equation in the form order of G is equal to order of center of G plus the summation runs over all the elements A in G into order of G divided by order of n of A. where the sum runs over representatives of all conjugacy classes with more than one element. We know that each term in order of G by order of n of A has the form p power k, with k is greater than or equal to 1. Hence, order of Z of G is equal to order of G minus the summation of A in G, order of G divided by order of n of A, where each term on the left is divisible by p. It follows that p also divides order of center of G, and hence order of center of G is not equal to 1. Let us see the Cauchy's theorem. The Cauchy's theorem is, let G be a finite group and let P be a prime number which divides cardinality of G. Then G has an element of order P. Let us prove this. We have to find an element A is not equal to E in G, satisfying A power P is equal to E. We prove this theorem by induction hypothesis on order of G. If order of G is equal to 1, then G is identity. The result is true. Let us assume that the theorem is true for all groups T such that order of T strictly less than order of G. For any subgroup W of G, W is not equal to G if P divides order of W. Then, by our induction hypothesis, there exists an element of order P in W. Thus, we may assume that P is not a divisor of the order of any proper subgroup of G. If A is not in center of G, since normalizer of A is not equal to G, then P does not divide order of normalizer of A. So, the class equation is order of G is equal to order of center of G plus the summation of normalizer of A is not equal to G, order of G divided by order of n of A. Since P divides order of G and P does not divides order of normalizer of A, so we have that P divides order of G divided by order of normalizer of A, which implies P divided by the summation of order of G divided by order of n of A. Since P divides order of G and P does not divides order of normalizer of A, so we have that P divides order of G by order of normalizer of A, which implies P divides the summation of order of G divided by order of normalizer of A. Therefore, order of center of G is equal to order of G minus the summation n of A is not equal to G, order of G divided by order of n of A. Since P divides order of G and summation of order of G divided by order of n of A, we conclude that P divides order of center of G. Thus, center of G is a subgroup of G whose order is divisible by P. But after all, we have assumed that P is not a divisor of the order of any proper subgroup of G. Therefore, the center of G cannot be a proper subgroup of G. The only possibility that the center of G is equal to G implies G is abelian. We have already proved that for an abelian group G, P is a prime number, then there exists an element A is not equal to E in G such that A power P is equal to identity. Hence proved. The next result, we will find the number of conjugacy class of Sn. The result is, the number of conjugate classes in Sn is P of n, the number of partitions of n. Let us prove this. For this, two permutations having the same cycle decomposition are conjugate. See here, delta is equal to the cycle A1, A2, A3 and so on A1. the cycle B1, B2 and so on, Bn2 and so on, the cycle X1, X2 and so on, Xnr. The next one is lambda is equal to the cycle alpha 1, alpha 2 and so on, alpha n1 into beta 1, beta 2 and so on, beta n2 and so on, psi 1, psi 2 and so on, psi nr. Lambda is equal to theta inverse delta theta. That is, two permutation in Sn are conjugate if and only if they have the same cyclic decomposition. Therefore, Sn will have exactly P of n conjugate classes. For example, conjugate of a given permutation, theta is equal to the cycle 1, 2, 3, the cycle 4, 7. Delta is equal to the cycle 5, 6, 7, the cycle 3, 4, 2. Since in theta, 5 goes to 5, 6 goes to 6, 7 goes to 4, 3 goes to 1, 4 goes to 7, 2 goes to 3. Theta inverse delta theta is obtained from delta itself. In delta, replacing 5 by 5, 6 by 6, 7 by 4, 3 by 1, 4 by 7, 2 by 3, then theta inverse delta theta is equal to product of the cycle 5, 6, 4, the cycle 1, 7, 3. Therefore, we can compute theta inverse delta theta by replacing every symbol in delta by its image under theta. Now, we have come to the end of the session. Let us recall the concepts once again. First, we have started this session by defining the conjugate. After, we move on to the conjugacy classes using equivalency relation. After that, we discussed some examples and results based on conjugacy classes, and then we came to the normalizer. By using the covered topics, we finally discussed the main part of this section, which is class equation. So, I hope this content is very useful for you. Let us see in the next session. Thank you.